Welcome back to the course Site 101X on Technology Evaluation. I'm Dan Fry, and in this segment I'm going to be taking you into some more details about choosing products in the product family. I'm going to talk about design of experiments. Now, design of experiments is a discipline concerned with planning experiments, analyzing data. So it covers both the early part of the process in which you're just thinking ahead to what you're going to do, and also the later part in which you try to understand what it means and make inferences. It grew as a subfield within statistics throughout the 20th century, but I would say that it's actually broader than statistics now, and it tells you about how to arrange factors. Now, factors are things that change in your experiment or else across your product family, and also levels, which are those values that the factors take. And I'm going to tell you about these three different options in the coming slides. Now, the full factorial design is an approach to experimentation which you can include every combination of all the factors in the study. So let's say that just very abstractly, you have three factors in a study, A and B and C. And let's say that A has three different levels. I'll call them low and medium and high. So if B and C were fixed, then there would just be three experiments, and you could consider them these blue dots here. Once you've visited those points, you can say that your evaluation is complete. Now, if you allow B to change, let's say that you start off with a low level of that, I'll call it minus, and then you change to a plus level, then in order to do the full factorial design, you would also have to change B to plus and consider low, medium, and high values of A. Not necessarily in that order. You could do these in any order, but you'd go from 3 experiments to 6. And then if you change C from its level, let's say minus over here, to plus on the back plane here, now you multiply by 2 again, and that's 12 experiments. So this experiment that I've shown with this cube is called the 2 to the 2 times 3 design. It requires 12 experiments or else 12 products in the product family. Now, I would consider this a resource-intensive approach, not because 12 is such a big number, but because as you add more factors to this experiment, it's going to grow very rapidly because you multiply by the number of levels every time you add a factor. So sometimes you need to find a way that's more efficient, and an orthogonal design is something that you might consider. This particular approach has a balance of pairwise comparisons. That's what orthogonal design means. And let's consider how that applies to this cuboidal representation down here. What you see is that 4 different combinations were included in this particular experiment, and 4 were left out. You did not make an evaluation there, or there, or there, or there. Now, why was this particular 4 chosen for evaluation and not some other 4? Well, it's because if you look at combinations of levels of A and B and C, for example, take a pair, A and B, and say A minus B plus. A minus B plus might be right at this location here. Take any other combination. Take C minus and A plus. That's combination here. And the key point is that when you make a combination of factors and levels, there's exactly the same number of evaluations at that point. And this can really help you to make the study efficient because you leave out a large proportion of the different combinations, but it's often infeasible for technology evaluation. And the reason is that we don't have complete control over the factors and levels. In technology evaluation, if, for example, you have a solar lantern, I don't have control necessarily over the size of the battery. That was a decision made by the manufacturer. So the factors levels are not under my control, and we can try to strive for an orthogonal design, but we may not reach it exactly. So we think about both those things that we strive for, like orthogonality, and the things we want to avoid, such as rank deficiency. Now, in rank deficiency, I want to give you a very concrete example. Let's look at 4 different wheelchairs that one might propose as a set of products as a product family. And let's consider a representation of this where each row represents a wheelchair and each column represents a product attribute of those wheelchairs. So consider the wheelbase being long. Here is a wheelchair with a long wheelbase, and here is a wheelchair with a relatively short wheelbase. So when we put them in our matrix, they have different entries, plus here and minus here, because they have different values. Same thing with whether or not the product has a single front wheel. This one has a single front wheel, so it gets a minus for 2 front wheels. This one over here has a short wheelbase, and it doesn't have a lever, so it gets a minus for lever, and it gets a minus for wheelbase long. Now, this particular set of text that I've put on the slide can be evaluated in MATLAB, and you compute the rank of the matrix family, and you'll find the answer that it comes up with is 2. The rank of this matrix is less than the number of columns in the matrix, so it has a rank deficiency, and that has an impact on our ability to make inferences from this product family. We could not, for example, tell whether or not switching to a short wheelbase would help improve the functionality of the product. Even if we had information about functionality of the product coming from our study, this study doesn't have resolution to give us that answer. So, to summarize, design of experiments is a discipline that helps us with the early part in planning and also with analysis of the data. It helps us think about the properties of our set of products as a group, as a set, or collectively. And it can have a big impact on our ability to draw conclusions, particularly if we have a problem with rank deficiency of our study. That concludes this segment, and I'll be interested in discussing this with you online.